does the coordinate xy work as a solution? So this concept brings in both some graphing and some algebra, and we're working with linear equations here. So you probably, or at this point, you should be somewhat familiar with this linear equation. This is in slope-intercept form. Slope-intercept form. I don't actually need that. And that's because each one of these letters tells us something important about the equation. So the M, it would be the slope. That's the rise or the run, basically how steep is the line. The B, that's the y-intercept. So that's basically where on the y-axis does the line cross. And then the x and the y. And so sometimes you're given it, let's use this example, y equals 2x minus 3. Notice that the m and the b are replaced with actual numbers. They are replaced with values, but the x and the y, those variables stay. And the reason for this is because this x and y, it's the same x and y that's in a coordinate point. But we don't have an actual number for these x and y's because there are multiple that could work in this equation. So if I were to graph this equation, y equals 2x minus 3, on my coordinate plane on the right, I would have a series of points, x and y values, that could plug in to the equation and still have it be true. These are called solutions to the equations, or sets of x and y's that would keep this true. If I have the equation graphed, I can tell right away if a coordinate is a solution to the line, or to the graph, because the line would cut through that point. But what we are working with today is being able to determine if a coordinate point is a solution or it is a point on a line without actually graphing it. So let me erase all of my numbers and we'll dive into this. All right, so I'm going to use the equation that I already had written, y equals 2x minus 3. And what will happen with a problem like this is you will be given a coordinate point and asked if it is a solution. So I'm going to use the example of the coordinate point 3, 3. Okay, so in this case, my x is 3 because that's always the first number in a coordinate point. And then my y just happens to also be 3. And I know that because y is always the second number in a coordinate point. So let's see what happens when I plug in 3 for y and 3 for x. And when I do this, I need to make sure that I am still following the correct order of operations, so PEMDAS, in order to know that my calculations were correct. So I replaced both x and y with 3, and now I'm going to solve based on PEMDAS. So first I need to multiply 2 times 3, that's 6. I'm going to bring down my minus 3, and my equals, and my 3. 6 minus 3 is 3, and I can see that plugging in 3 for x and 3 for y led me to what is still a true equation. 3 does equal 3, so I would say yes. 3, 3 is a point on this graph. So I'm going to write that down here so we don't forget. We're going to do 2 more examples and then we'll see whether or not we were correct by graphing. So let me erase this and we will do another point. So this time, let's test a point that I already know is not going to work. So for example, let's test the point 4, 2. And we're still using the same equation, y equals 2x minus 3. So let's see if this x and this y would work as a solution or as an answer set to this equation. So I'm going to plug in 2 for y. So I have 2 equals 2 times x, and x is 4. So 4. and then still minus 3. PEMDAS means I must multiply before I subtract. So 2 times 4 is 8. I'm going to bring down my minus 3, and I can't forget my equals and my 2. Now when I simplify the right side, 8 minus 3, that is 4. Wait, 2 does not, oh, that's not 4. Hold on, sorry about that. I knew that was wrong there. 5, let's try that again, 5. But still, 2 does not equal 5. So no, this is not a possible solution. So I'm going to keep that in red over here, and we'll see how we can tell later how that's not a solution. So let's graph. Well, I do 2 examples, one yes and one no. Let's graph this equation and see if we were correct in our determining of whether these 2 points are solutions. So I'm going to graph y equals 2x minus 3. So that means my slope will be 2. So I will rise 2 and run 1. And my y-intercept is minus 3. So I'm going to start down here at negative 3. And I'm going to go up 2 and over 1. Up 2 over 1, up 2 over 1. I'll continue all the way up, and then continue the line in the other direction as well, extending these, trying to keep them as straight as I can. And now I'm going to graph these 2 points. So let's put a dot at 3, 3. That's here, and you can see, yes, the coordinate point 3, 3 is on the line when we graph it from the equation. So we were correct in our calculations that 3, 3 is a solution to this equation. This is a value of x and a value of y that when plugged into the original equation, keep it true. But notice when we tested 4, 2, when I graph 4, 2 on my coordinate plane, that point does not lie on our line. And so that's why when I plugged in 4 for x and 2 for y, it ended up with a non-true equation, an incorrect equation. This just isn't true. So no, the coordinate point 4, 2 is not a solution for this equation, for it is not on the line. So in order to determine whether a x and y coordinate or just an x and y value, you can ignore the whole idea of a graph entirely if you just plug in the x coordinate for the x variable in your equation and then plug in the y coordinate for the y variable in your equation, and then just make sure that you follow the rules of PEMDAS until you cannot simplify anymore. If what you have left is true, then yes, it is a solution. If this is false, then no, that x and y value is not a solution.